The miniaturization of optical systems is a persistent challenge across the electromagnetic spectrum. Recently, the concept of nonlocal metamaterials has been proposed to contract distances between optical elements, thus shrinking the volume of these systems. This paper presents the first experimental demonstration of a spaceplate in a real-world optical system, a microwave gradient index (GRIN) lens antenna. The spaceplate, formed by three suitably coupled Fabry-Perot cavities employing partially reflecting metasurfaces, has a thickness of 17.1 mm and acts as 120 mm of free space, resulting in a compression factor of approximately 7. The GRIN lens antenna consists of a dielectric GRIN lens and a rectangular, linearly polarized horn antenna source. The lens is designed with a focal length of 200 mm, and its edges are illuminated at 17.1 dB and 14.8 dB below the axial illumination level in the E and H planes, respectively. The lens is fabricated from high-impact polystyrene (HIPS) using a 3D printer, with a relative permittivity value of 2.45 and a dielectric loss tangent of 1.1 × 10⁻³ at 23 GHz. The gradient index profile is discretized into 8 concentric rings, each with its own relative permittivity value that decreases from the center to the outermost ring. The effective permittivity is controlled by varying the volume percentage of air to plastic for each ring, achieved through the infill percentage parameter in the 3D printer's slicing software. The spaceplate is inserted between the lens and the feed antenna, bringing the focus closer to the lens from 200 mm to 117 mm, while keeping the focal length of the system unchanged. The distance between the lens and the feed antenna is reduced from 150 to 67 mm. The final device is characterized by means typical in antenna metrology. The far-field radiation patterns, cross-polarisation, directivity, gain, and efficiency are measured in a near-field antenna range and the optical systems with and without the spaceplate compared. It is found that the radiation patterns from a conventional and space-squeezed antenna are very similar, with a very low cross-polarisation, and only a minor increase in the side-lobe levels when introducing the spaceplate. The directivity of the space-compressed antenna is comparable to the uncompressed one, while the efficiency and thus the gain of the compressed antenna is reduced by approximately 35%. Finally, possible routes to improvement in the future are discussed. The paper presents a novel approach to achieve a threefold increase in the effective focal length of a microwave lens, using a multi-cavity spaceplate composed of Fabry-Perot resonators. This is achieved through the introduction of a multi-cavity spaceplate between two identical lenses in a twin-lens 4F quasi-optical setup. The spaceplate consists of three air-filled cavities, C1, C3, C5, and two dielectric-filled cavities, C2, C4, with specific thicknesses tuned to achieve transmission maximum at approximately 23.5 GHz. The compression factor for the three-cavity spaceplate is slightly higher than that of a single isolated Fabry-Perot spaceplate, resulting in an enhanced effective focal length. The performance of the spaceplate is validated by simulating its transmission coefficient for both transverse electric (Te) and transverse magnetic (TM) polarization states. The dispersion plots show a parabolic shift of the resonance with angle, indicating the spaceplate's ability to maintain the phase of free space even at frequencies away from the resonance. The compression factor as a function of frequency is also plotted, highlighting the 4 frequency points of interest. Experimental validation is conducted using a twin-lens 4F quasi-optical setup, where the spaceplate is introduced midway between two identical standard gain horn antennas. Measurements of the transmission coefficient with and without the spaceplate are conducted, demonstrating the effectiveness of the multi-cavity spaceplate in extending the focal length of the microwave lens. The results confirm the simulated predictions, showcasing the potential for this design to significantly enhance the performance of microwave imaging systems. The research paper presents a novel approach to enhance the performance of a millimeter wave antenna by incorporating a spaceplate between the feed horn and a GRIN lens. This setup aims to reduce the size of the antenna while maintaining its directivity and efficiency. The paper discusses the experimental setup, measurement techniques, and results, including radiation patterns, directivity, efficiency, and reflection coefficients. The introduction of the spaceplate reduces the distance between the horn and the GRIN lens from 150 mm to 67 mm, preserving the main beam's shape despite the reduced separation. The radiation patterns show an increase in radiation levels outside the main beam for the lens and spaceplate squeezed lens antennas, attributed to reflections at the air-dielectric interface for the lens and from the spaceplate at angles over 30 degrees for the spaceplate-based antenna. The prominent side lobes at plus or minus 153 degrees in the elevation plane of the spaceplate-based antenna are reflections of the side lobes of the source horn antenna located at plus or minus 27 degrees. Cross-polarisation levels are subtly influenced by the presence of the spaceplate, but the overall cross-polarisation level at the bore site remains close to 30 decibels. The directivity, efficiency, and reflection coefficient of the antenna under test, AUT, are compared as functions of frequency. The efficiency of the AUT was calculated using the direct comparison method, and the reflection coefficient indicates that the spaceplate is well impedance matched to the rest of the elements in the frequency range of interest, 22.7–23.6 GHz. An important consideration when placing a spaceplate close to an electromagnetic source, such as a feed horn antenna, is its influence on the source's properties via reactive near-field interaction. This results in an alteration of the antenna's radiation pattern, as the source antenna and the spaceplate become a single electromagnetic component and are no longer separable in their function. In the experiment with the spaceplate inserted between the lens and the feed horn, the axial distance from the edge of the horn to the spaceplate is 25 mm, corresponding to electrical lengths of approximately λ4. This setup demonstrates the potential for size reduction in millimeter wave antennas without compromising their performance. Here is a combined summary of pages 7 and 8 of the research paper. The authors have experimentally demonstrated a size reduction of a microwave optic system, specifically a GRIN lens antenna, using a spaceplate. The spaceplate is capable of compressing a slab of free space 7 times as thick, reducing the length between the lens and its focus by almost a factor of 2 while keeping the focal length of the optics unchanged. The radiation patterns of the squeezed system are very similar to those of the uncompressed antenna, with a very low cross-polarization, similar directivity, and a minor increase in side-lobe levels. However, a considerable degradation in efficiency of around 35% is attributed to losses in the dielectric materials used to support the individual metasurfaces. The authors suggest that the ripple in the main beam of the radiation pattern of the spaceplate-enhanced antenna might be in part caused by the reactive near-field interaction between the horn antenna and the spaceplate. The small effect does not appear to alter significantly the directivity of the antenna, which can also be explained by the varying transmittance of the spaceplate within its numerical aperture. The authors conclude that the space-compressed antenna operates with a minor reduction in directivity and a considerable degradation in efficiency, mainly due to dielectric losses in the substrates of the cavity mirrors. They propose that a fully metallic solution would be preferable to rectify this effect, which may be more difficult to achieve. The authors believe that space compression metamaterials will be an important route towards miniaturized optical devices operating in the microwave region. The authors also discuss the potential of spaceplates in various applications, citing previous works on holographic pancake windows, folded reflect array antennas, and multifunctional spaceplates for optical aberration correction. They highlight the importance of understanding the performance limits and implementation of spaceplates at microwave frequencies and the need for low-loss dielectrics or fully metallic metasurfaces to improve efficiency. This supplementary document provides detailed information on the design, simulations, and measurements of the spaceplate-based GRIN antenna. The experimental setup for material characterization is shown in Figure S1, which includes a spaceplate, low-permittivity foam, collimating lenses, source, and detector. This setup was used to measure the frequency dispersion of the spaceplate and 3D printed materials, with results presented in Figure 3, D, and E of the main paper. The GRIN lens is composed of 8 regions with varying effective permittivity, as described in Table S1 and depicted in Figure S2. Each region has a different volumetric filling fraction and calculated relative permittivity, which allows for the desired gradient index profile. The spaceplate is analyzed and designed as a composition of 6 partially reflecting mirrors, forming 3 individual Fabry-Perot (FP) cavities. Figure S3a introduces the unit cell of the whole array structure deposited on a microwave substrate, with period P and hole size A. The reflectance of the sheet as a function of frequency for normal incidence and 30 degrees incident angle is shown in figure S3b, highlighting the small difference between T and TM polarization due to the Fresnel reflection coefficient. By stacking 2 such partial mirrors, a single FP cavity is formed, as depicted in figure S4a. The thickness of the air gap between the sheets is denoted as d. The magnitude and phase of the simulated transmission coefficient are given in figure S4b and c as functions of incident angle and frequency, obtained through finite element solver ANSYS HFSS. The effective thickness of free space that the spaceplate replaces is evaluated by fitting a free space dispersion arg express IK def cos theta to the simulated phase dispersion. This fitting is conducted for each frequency over the operating range of the spaceplate, corresponding to the numerical aperture Na equals sin theta max, where theta max represents the maximum incident angle accepted by the spaceplate, 20 degrees. The compression factor C equals def DSP is calculated using the thickness of the spaceplate DSP, 5.7 mm, and its variation with frequency is shown in figure S5a and b for T and TM polarization states, respectively. The research paper presents a comprehensive analysis of the simulated properties of a single Fabry-Perot cavity, focusing on both T and TM polarization states. The unit cell schematics in figure S4a illustrate the basic structure of the cavity, which is essential for understanding its optical properties. In figure S4b and c, the dispersion plots for T and TM polarization states are presented, respectively. These plots show the magnitude and phase of the simulated transmission coefficient as a function of frequency. The plots reveal distinct band gaps and passbands, indicating the selective nature of the cavity's transmission properties. This selective transmission is crucial for applications such as optical filtering and sensing. Furthermore, the paper discusses the calculated compression factor of a single Fabry-Perot cavity spaceplate, shown in figure S5a for T polarization and in figure S5b for TM polarization. The compression factor is a measure of how much the light is slowed down within the cavity compared to its speed in vacuum. The compression factor is a critical parameter in determining the performance of the cavity as an optical resonator. The analysis demonstrates that the compression factor varies significantly with frequency, particularly near the band edges where the transmission coefficient approaches 0. This variation suggests that the cavity can be optimized for specific applications by carefully designing its dimensions and material properties. Overall, the study provides a detailed understanding of the optical properties of a single Fabry-Perot cavity, highlighting its potential for various photonic devices. The findings presented here could be beneficial for researchers working on the development of high-quality optical resonators and filters.